Okay, so far we've been talking about conservation of energy. We're going to review really quickly. So for conservation of energy, specifically when there is no friction present, we can assume that the mechanical energy in the system is conserved. Can someone remind me what mechanical energy is? Or possibly what types of energy would be considered mechanical? Christian?
Well, isn't mechanical energy like the motion, like when energy is like in motion or an object's in motion?
Okay, so we have mechanical energy. Under that category, we have the energy of motion, which is kinetic energy. Okay. So one type of energy that's considered to be mechanical is objects or system moving, which we call that kinetic energy. KE. Okay. What else? Go ahead, Christian.
Would potential energy also be mechanical energy as well?
Exactly. So it's the energy of an object's motion or its energy due to its position. Right? We have two different types of potential energy, which is the energy of an object due to its position. Okay, we talked about gravitational potential energy, which is the energy due to an object's position relative to some zero line or some zero height that we assign in our reference frame, or potential energy that is stored due to the position of a spring, meaning the stretch or compression of a spring. So the types of mechanical energy that we have is either energy of motion, which is kinetic energy, or the energy due to an object's position, which is potential energy. Specifically, we're talking about two types: gravitational potential, which is position relative to some zero line, and elastic potential, which is energy stored due to either the compression or stretching of a spring. So this is definition of what mechanical energy is. Okay, and we can set the initial mechanical energy of the system equal to the final mechanical energy of the system if the system is assumed to be frictionless, because that means no energy is converted to thermal energy due to friction. Okay, so our general procedure here, right? We want to identify what the initial height is, or where our zero line will be. We want to identify what the velocity of the object is, and if there's a spring involved, we want to figure out the compression distance, x, at 2 points in the object's motion, which we will call either initial or final. And we will examine the energy transfer between those 2 points, or those 2 positions. Okay, so the examples that we had skipped were the concept examples. Reason being is because they're a little bit more difficult. They do not involve numbers. They involve the concepts. So we're going to start out today just talking about a few of those. In the first concept example from the notes, it was concept example number 4, which is right below example number 5 on the second page. We have a mass that's pressed against a horizontal spring on a, keyword, frictionless surface. After being released from rest, the mass acquires a maximum speed v and a maximum kinetic energy k. If the mass was initially compressed twice as far, okay, so they're asking us to compare two situations. We're going to first write down the information given to us in situation 1. So a mass is pressed against a horizontal spring. Okay, so up here I have my first image. It's being released from rest. So that tells us that V initial is 0. It's released from rest. Once it's released, so once it leaves the spring, it's going to exit the spring and begin to move at some velocity, v. So we're told that v final is v. From our initial point to our final point, the height of the object stays the same. So we can call, right, the lowest path in the object's motion, we want to call that the 0 line, where h is 0. So h final of the object is 0, h initial of the object is 0. Okay, we could call it whatever we wanted. We could say that it starts at 5 meters and ends at 5 meters from the ground. Technically, it'll cancel out because it starts and ends at the same height, so there is no change in the gravitational potential energy. Okay, it's easier to assign the lowest point in the object's path as 0. Okay, so that's what we're doing here. We're going to say that its initial height and its final height, it's along the surface of the table or the ground. We assign that height to be 0. Okay, and it's compressed some displacement initially. We're told that the initial compression, h initial, is just x. We're not given an exact value, so we're just going to call it x. So it's compressed some distance x, so the spring will store energy to do that compression. It starts with no gravitational potential energy and no kinetic energy. It's going to leave the spring and slide across the surface, gaining a maximum velocity of v. Okay. In our second situation, we're told that the mass is now compressed twice as far. So our initial situation is going to change. This compression distance of the spring, x, is twice as far. So in our second situation, x initial is 2 times x, right? It's coiled or compressed twice as far as before, 2x. We need to figure out how the final velocity is going to change based on the change in the compression. Okay, so the situations are virtually the same except for in the second situation, it's going to be compressed, the spring will be compressed twice as far. Okay, so object will still be, when it's compressed, it'll start at rest. When it's released, it's going to move across the surface with some velocity. We need to figure out how that velocity changes. Okay, so let's take a look here. Our answer choices are maximum speed will be 2 times v, and maximum kinetic energy will be 2k. Maximum speed will be 2v, maximum kinetic energy will be square root of 2k. Okay, so what we're asked to find is velocity and kinetic energy. So you want to relate the velocity and kinetic energy from situation 1 to situation 2. Okay, so in situation 1, right, let's take a look at what our equation would look like. So in situation 1, initially, what kind of energy do we have? So in the initial segment of situation 1, what type of energy do we have?
I was gonna say kinetic or mechanical energy.
Initially, is the object moving?
It looks like it. Like with the arrow. Or no, it's not, right? Because the velocity initial is 0, right?
Right. So the final velocity of the object is going to be some value, which we are told is v. But initially, it starts at rest. So initially, it won't have any kinetic energy. Andrew?
It's potential energy, right?
Okay, good. What type of potential energy?
It's not gravitational, but it's the other one.
Okay, the other one. So not gravitational potential energy. It's elastic potential, exactly.
Yeah, that one.
There we go. So my stylus is a little slow here. But kinetic energy initially will be 0 because V initial is 0. So kinetic energy initial will cross out of our equation. Height initial and height final are both 0. So potential energy, gravitational potential, will cross out on the left-hand side for initial. But our spring is compressed initially. So we're going to have some elastic potential energy initially. Okay. After, so on the final situation, or final segment of situation 1, what type of energy do we have once the object leaves the spring and is moving across the surface? What type of mechanical energy will we have finally? Anna?
Kinetic.
Kinetic energy, only kinetic energy, right? Object's no longer attached to the spring is no longer compressed, so kinetic elastic potential energy will be 0. It's still at the same height that it began, so there will be no gravitational potential energy. There's only kinetic energy. So all of the energy stored in the spring, due to its position, is converted to kinetic energy after the spring and the mass are released. So we'd have 1/2 times k times x squared. It's the equation for elastic potential energy. That's going to be equal to the kinetic energy, which would be 1/2 mv squared. Okay, for situation 2, the only thing that's changing in this situation is that we're starting out with double the compression. So mechanical energy is still conserved. We still start with only elastic potential energy, and we end with only kinetic energy. But this time, the x in our equation is going to be doubled. Yikes, this is so slow. Now you guys know why I try and record videos beforehand, because I have to pause. That video takes like two times as long to actually write, because I have to pause it, because the screen freezes. It's a mess. And of course, I just messed that up. Yikes. There we go. Okay, so the only thing that's going to change in the second equation is now x is actually equal to 2x instead of just x. So in our elastic potential energy equation, we're going to plug in 2 times x, double the compression distance, square it, equals 1/2 mv squared. And we're looking at how v is going to change. Okay, so we're comparing these two situations. So if our compression distance doubles, does this side, or actually let's go over here. So if x doubles, this side of the equation is going to change by what factor? So elastic potential energy is equal to kinetic energy in both situations. But in situation 2, we have double the compression distance. So what's going to happen? Okay, this factor of the equation is going to increase by 4, right? 2 squared is 4. So this side of my equation, I'm going to have 1/2 k times 4x squared. Because the compression distance is 2x, you have to square the entire compression distance, so you get 4x squared. Okay, and then we can simplify. If it's easier, you can solve for v. It makes it easier to look at. Or you can think about what factor the equation is going to change by. So to simplify this here, right, my 1/2 will cancel on both sides. I have k times 4x squared is equal to mv squared. I need to solve for v, right? The question asks us about speed. So I'd have 4, just going to rearrange this a little bit, 4k x squared divide both sides by m, and then take the square root. Okay, so v is going to be equal to the square root of 4 k times x squared over m, which can be simplified a little bit. How could we simplify that expression?
Can't you take an x out since it's x squared?
Okay, you can take an x out. What else could you take out?
Oh, the 4?
The 4, right? So square root of 4, we get 2. Square root of x squared, we get x. And then we'll have to keep the k and the m in the parenthesis, or in the bracket, because we can't take the square root of those. Okay. Versus for our first situation, when we solve for v, the 1/2s are going to cancel. We'll divide both sides by m. We get the square root of k x squared over m. And then the x squared over here can also come out of the radical, just like we had simplified before. So comparing these two velocities, when x is doubled, what happens to the velocity? So situation 1, right? The spring is compressed by x. The velocity is x times the square root of k over m. When the spring is compressed 2 times x, double the initial compression, velocity is 2 times x times the square root of k over m. So how can we compare these two velocity equations? What happens to the velocity when x is doubled? Anna?
Velocity doubles too.
Velocity doubles too. Okay, so the entire equation is going to increase by a factor of 4. So kinetic energy would increase by a factor of 4, but the velocity itself will double if the spring compression doubles. Okay, so our answer here is D. Velocity doubles. We solve for V, it's 2 times the initial amount because we took the square root. But the kinetic energy is going to increase by a factor of 4. Because, right, compression distance is squared. Okay, so the entire kinetic energy will increase by a factor of 4, but the velocity itself, because it's squared, is going to increase by a factor of 2, or double. Any questions there? Okay, so I'm going to have you guys try concept example number 5 for homework. Okay, it's similar, very similar to this, except we're looking at gravitational potential energy and kinetic energy instead. Okay, the answers to the previous homework problems are also posted in Google Classroom. So we'll pick back up in class tomorrow with concept example 5, which I want you guys to start or give it a try yourself tonight before we get to class tomorrow.